the same experience, sort of looking at STAR from the NERSC point of view, which runs a bunch of these production systems, was we did a fairly intense study on Eucalyptus, and Argonne did the same on OpenStack. And we identified significant gaps and challenges that were in current open source virtualized cloud software stacks as you scaled up. It works really well when you're doing a few dozen virtual machines, but you start running into all kinds of issues as you go in to higher scales. So the diagram that's here on this slide is essentially the Eucalyptus architecture diagram, and you have something called a cloud controller, which connects to the cluster controllers and storage controllers in each cluster, and the node controllers are where the VMs are located. So that you have as many node controllers as you have number of nodes in the cluster, essentially. So in scalability-wise, the VM network traffic was a major issue because it was all routed through the cluster controller, at least in the version of Eucalyptus that we were using. There was also a limit on the concurrent virtual machines that we could launch due to a messaging size limit. That bug was eventually fixed, but these were challenges that we worked through. We were early users of some of this software. And it required a fair amount of tuning and tweaking and figuring out what drivers to use, what worked best, how to get the best performance. And we were constantly tweaking the system to get all that. There were problems because it didn't quite, the virtual machines, we were not able to get like the Nehalem CPU, advanced CPU instructions to show up in the VMs. So when we were doing the performance study, we had to do a bunch of hacks into Eucalyptus scripts, make sure those got transmitted back into the VMs. And some of the software sort of controls your cluster, so it doesn't work very well when you have other competing services that might be on a cluster, including we had our own DHCP server. So all those kind of problems were definitely an issue. One of the other things that is important to us, because we run a supercomputing center here, is this allocation and accounting and logging and monitoring, right? These are issues we have to keep in, both for keeping up with DOE policies, but also being able to track what's happening on these VMs and stuff. And it was hard to ensure fairness since the allocation was essentially a first come, first serve. It was true that we didn't have a whole number of users, so we could sort of do this offline, out-of-band negotiation that happened, but it definitely was a problem when we were trying to scale up. And then there was just the limited logging and monitoring made it very difficult sort of to track back what had happened, why did the VMs fail, what's going on, and things like that. So the other advantage that a lot of people talk about is the on-demand access for scientific applications. That is, you can go and get a virtual machine as soon as you need it. And batch queue systems in supercomputer centers are a big problem because you have long wait times on batch queue systems. So that was what we heard from our users. So we did a quick study where we said, okay, so most of the capacity that cloud computing comes, Amazon's able to provision is because they do a consolidation across different users. So the peak usage of one user does not always match with the peak usage of another user. So they're able to sort of share the resources and plan for those situations. So we looked back at our logs from Franklin, which is our supercomputer center. So was our biggest supercomputer at that point. Hopper is right now the biggest supercomputer here. And we basically did a study and where we said, okay, if we were to meet every job request as they arrived, what would our capacity of our cluster of our system need to be, right? So it may not be very clear on the slide here, but there's a small red line, which is the actual capacity of Franklin, below sort of 50, right below the 50 marker on the y-axis. So there is about 38,000 cores or so of Franklin. And you can see the spikes here, right? So if we were to satisfy every user, we sort of have to provision at the 400,000 capacity, and then we'd have all that white space in the middle bed, which would essentially be unused cycles. So the reality is on-demand access for scientific applications might be difficult, if not impossible, mostly because if all the white spaces would get filled because we have users who would come in and run jobs. So there's never sort of ideal cycles available to the users. So that's a challenge that would definitely, and most times on-demand comes from some kind of sharing of resources. So you could have premium level support of services to help give some users immediate access, use checkpoint restart as ways to preempt some jobs and gives others some priority. So the other thing that we always heard was clouds are definitely cheaper. So we did a large amount of cost calculations to see different situations, different scenarios, and the Magellan report has a more detailed analysis of this cost study. But here's one example that I'm putting up here on the slide where we assume that we have 85% utilization and 0 growth in our archive and file system data, which is not true. And then, so HPSS is our archive system. So we translated that to costs that would cost on Amazon's cheapest stuff, right? Like cheapest similar configuration. So if you get a reserved allocation on Amazon, you get a slightly lower rate. And it's true that Amazon might provide you even lower rates if you were to negotiate a long-term contract with them. But what we have on the slide is only it only captures about 65% of NERSC annual budget. There's no, we don't consider the whole consulting and system administration and support costs that are part of the NERSC budget here. And this is significantly higher than the NERSC budget, 4x higher at this point. And this does not include the 2x to 10x performance impact that I talked about earlier, right? So things would run significantly slower in these environments, and that has a cost associated with it. So we don't consider that. So clouds, the conclusion was essentially for us that clouds is a business model. There's definitely a lot of things that clouds provide here that can be applied at HPC centers, right? So one of the things we did was to tease out these factors and say, okay, so what's the difference between traditional enterprise IT workloads and HPC centers? And you see the typical load average is definitely one of them. The bounded computing requirements that I talked about. Web workloads, you know, Amazon has a peak period of when they, in the Christmas season, because they have to sell a lot of stuff during that season. But there's all other times that they know what their sort of requirements are. They know how much they're going to need, how much resources they're going to need. Whereas HPC centers and science workloads are virtually unbounded requirements. They will always find larger and more complicated problems to simulate or analyze. There's also a difference in how the scaling happens. There's a lot of scaling approach in enterprise IT and cloud environments of scaling in, where your emphasis on consolidating in a node, mostly because a node for these workloads does not use all the resources. They don't typically run at 100% CPU, 100% use most of the memory, and do a lot of I/O. So they're able to sort of place multiple VMs on there that do different things and be able to use the node to its maximum. But most of our applications tend to be more intensive, and they have a scaling approach that is run in parallel across multiple nodes. And so the approach is a little different here. And you see that the software stack is basically tuned to meet the needs of these specific workloads, right? So clouds have a more flexible user-managed software stack, whereas HPC centers today have access to parallel file systems, low latency, high bandwidth interconnect. They come with pre-tuned, pre-installed software stacks for performance. Performance is a big thing in HPC centers. And so it's true that there are some features of cloud that our users would like. They would like more control on their software stacks, But they're not restricted to having to be on virtual machines. They can be on bare metal, and we're looking at ways to provide some of these at our center here and use some of the technologies in slightly different ways from how they've been used. So I think that's a key takeaway, that cloud, as the commercial sector talks about it, is really not an out-of-box solution that scientists can just go pick up and use. There's a significant learning curve there.